Good morning, students. Um, Today I will cover my lecture on Hamiltonian cycles. Actually, this is a backtracking technique, backtracking application. Actually, we will use the backtracking technique in explaining the Hamiltonian cycles and counting the number of Hamiltonian cycles in the graph. So let's look at the problem. If a graph is given, and let's say I'm taking this example of 6 vertices, right? If a graph is given to you, and if you start from a vertex, you visit all the vertices once and come back to the same vertex. So that's what I have written here. If a graph is given, start from a vertex, visit all the vertices in the graph and reach to the same vertex, or what we call as a tour or visit all exactly once. So this is called a Hamiltonian cycle. Now, what is the problem at hand? We need to check, first of all, in a graph, we need to check whether there is a Hamiltonian cycle possible in the graph or not. Hamiltonian cycle means going from one vertex and reaching to the same vertex after traversing through all the vertices once. And we also need to know if there is a Hamiltonian cycle, then how many Hamiltonian cycles are possible? And what are the different, how many Hamiltonian cycles are possible? 1, 2, 3, 4, how many? And what are the different Hamiltonian cycles? What are the different Hamiltonian cycles means going from 1, 2, 3, 4, 5, going from 1, 6, 5, 2, going from 1, 3, 4, like this. You have to tell what are the traversing tracks, what are the cycles that how you will make a Hamiltonian cycle. All right. So this problem actually looks like a traveling salesperson problem, in which, or in the traveling salesperson problem also we do the same thing. We traverse from starting from one node, we traverse through all the nodes, and we reach to the same node. But traveling salesperson problem is a minimization problem. Minimization problem in the sense that, let's say we start from 1, we need to know the cost of reaching to all the vertices, the minimum cost of reaching to all the vertices. That's what is the traveling salesperson problem. So it is a minimization problem that we need to know the minimum cost of reaching from a vertex to all other vertices. What is the minimum cost? But in the case of Hamiltonian cycle, we are not concerned about the minimization problem. So we want to know how many cycles are formed and what are those cycles. So in a graph, you have to write an algorithm from which, with the help of which you can know how many Hamiltonian cycles are possible and what are those Hamiltonian cycles. I have taken this example of 6 vertices. So first Hamiltonian cycle is going from 1 to 2 to 3, going from 1, 2, 3, 4, 5, 6, and coming back to 1. So this is one Hamiltonian cycle. The second Hamiltonian cycle is 1, 2, then coming to 6, 5, 4, 3, right? And this one. So that means this is the second Hamiltonian cycle. Third Hamiltonian cycle possible, there can be many, but I'm giving you certain examples. 1, 6, 2, 5, 4, 3, and then 1. So this is another Hamiltonian cycle. But let's look at this first Hamiltonian cycle, 1, 2, 3, 4, 5, 6, and then 1. Right? I have taken the example of starting from 2, 3, 4, 5, 6, and 1, and then coming. So actually this cycle is the same cycle as the first cycle I have explained here. Because the rest of the only the thing is that in the first example, the starting node is 1, but in the second example, starting node is 2. So this is a kind of duplicate cycle. Basically, the cycle remains the same, but only thing is that we are just, so this will not be considered as another Hamiltonian cycle. So it is the same cycle as the first cycle. That's what the point is. So you have to you cannot consider this as another Hamiltonian cycle. Okay. So let's look at this example now. If you look at this graph, you will see that whether you starting from 1, let's fix the starting node as 1. Starting from 1, are you able to find any Hamiltonian cycle? No, there is no Hamiltonian cycle. You cannot visit all the vertices once and come back to the same vertex. For example, if I start from 1, 3, 5, so I will have to come back to 3, right? So this graph does not have any Hamiltonian cycle. So this kind of point, which is actually the junction point of the left side and the right side of the graph, these points are known as the articulation points. So whenever a graph has an articulation point, so that graph, there is no Hamiltonian cycle in that graph. So you cannot have a Hamiltonian cycle there. Okay. The problem at hand now is to find out how many Hamiltonian cycles are there in the graph and what are those cycles. So let's take an example and let's see how backtracking can help in finding out how many Hamiltonian cycles are there and what are these Hamiltonian cycles. I have taken this example of 5 vertices, 1, 2, 3, 4, 5. 5 vertices are there, and this is the adjacency matrix of this graph, meaning by starting from 1 to 1, there is no self loop, so the cost is 0. Going from 1 to 2, the cost is 1. That means there is an edge from 1 to 2. Going from 1 to 3, again there is an edge. This edge is there for 1 to 3. This 4 is 0. Going from 1 to 4, 0 means there is no edge. Going from 1 to 4 directly, there is no direct edge. So that's how the adjacency matrix is defined. All right. I have already explained the problem. We need to know how many Hamiltonian cycles are there using a program, basically. Not actually finding out from the graph. We need to write a program, basically, or an algorithm, which should be able to find out how many cycles are there. To start with the problem, we will take an array, right? The array size is the number of vertices. Okay, array size is equal to the number of vertices. So X is the array, and we will initialize the array with all zeros. All right. Okay, initialize all values are 0. Initially, all values are 0 in the array. Now, we will fix the starting vertex. And in this example, I have fixed, for example, X of 1. I have made it 1. So that means I have fixed the starting vertex. If I will not fix the starting vertex, in that case, I will get this kind of problem, 2, 3, 4, 5, 6, 1, and 1, 2, 3, 4, because these two are same cycles. Had I fixed 1 as the starting vertex, this cycle will never exist. So, right? So fixing the starting vertex, we don't want duplicate Hamiltonian cycles. So we fix the starting vertex. All right. So we make the first entry corresponding to vertex 1 as 1. All right. Now let's look at, so we fix the starting vertex. So my entries in the array are 1, 0, 0, 0, corresponding to the other arrays, other vertices also. Now, what we will do in the array, we will start incrementing this second position of the array, starting from 1. 1, 2, 3, 4 means these are, we are incrementing vertex wise. So we make 1 first of all, but since 1 is already present, so this is not a valid entry. The algorithm will try to put 1, but it already is there at X of at the first position. So 1 is not a valid entry. So it puts 2 here. So once it puts 2, this is a valid entry, right? 1 cannot come at this position. 1 cannot come because it is a duplicate value which already exists in the previous entries in the array. So 1 cannot come. 2 is there. It is a valid entry, no doubt, but we will also have to check whether there is an edge from 1 to 2 or not. So that we will check from the adjacency matrix. So this is vertex 1, 1 to 2, there is an edge. So this is edge is also there from 1 to 2. So this entry is valid. So we will actually backtracking, finding the Hamiltonian cycles using backtracking is equivalent to depth first search. All right, we will see how. So we started from vertex 1, we reached to vertex 2 as per the second entry of this array. Now we come to the next entry. We will start again from 1. 1 is a duplicate entry because 1 already exists here. We will make it 2. I have tried to explain here. We will make it 2. 2 is again not a valid entry because 2 already exists in the previous positions. I will make it 3. It's a valid entry, but I will have to check whether there is an edge from the previous entry to the present entry. That means from 2 to 3, I will have to check whether there is an edge present or not. So that means from 2 to 3, it is 1. So that means an edge is present. So the algorithm takes the graph or takes the search from 1 to 2 to 3. All right. Now we come to the fourth entry. We will make it 1. It is a duplicate entry. We will make it 2, again a duplicate entry, make it 3, again a duplicate entry. We will make it 4. So 4 comes here, valid entry, no problem because no duplicates are there, but we will have to check whether there is an edge from 3 to 4 or not. How can we check? We will check it from the adjacency matrix. From 3 to 4, yes, it is 1. So there is an edge. So it's a valid entry. So the graph takes will take the graph further to node vertex 4. All right. Then we go to entry number. Then we go to fifth entry. Again, the same procedure. The algorithm will run values from 1, 2, 3, 4, and then 5. 1, 2, 3, 4 already exists, duplicate values, and 5 is okay. But we will have to check whether there is an edge from the previous entry, which is 4. We will check whether there is an edge from 4 to 5. Let's check. From 4 to 5, yes, there is an edge. So 4 to 5 is a valid entry. These are the values in the array, and this is the graph of. And finally, please remember this. I have discussed 2 points. First point is that there in the array, there should not, when we are making an entry, there should not be duplicate values. The second point, important point, is that you have to check whether the edge exists from the previous entry or not. If these 2 are satisfied, then we will have to, in the end, after all the entries are filled, we will have to check the final thing, which is whether there is an edge from 5 to 1, because it has to go back to 1, then only it's a Hamiltonian cycle. Whether from 5 to 1 the edge exists or not. So from 5 to 1 the edge exists. The value here is 1. So this is a Hamiltonian cycle detected. And if you go from 1, 2, 3, 4, 5 in the graph, and come back to 5, come back to 1, it's a valid Hamiltonian cycle. And we will print this result. We will print the values of 1, 2, 3, 4, 5, and 1. So that means it's a Hamiltonian cycle detected. Okay, what should be checked in the algorithm? It should not take duplicates, as I have already explained. When a vertex is selected, for example, 2 was selected, 3 was selected. When a vertex is selected, there should be an edge from the previous vertex. This is very important. While writing, I will explain in the algorithm, and you will have to write the algorithm in such a way that these 2 conditions are met. And the third condition is that if on the last vertex, there should be an edge to the first vertex. If so, that completes a Hamiltonian cycle. I hope the things are clear. Let's take because you have to detect, there can be present more than one Hamiltonian cycle also in the graph. So you have to detect in this problem, you have to detect how many Hamiltonian cycles are there and what are actually the cycles, going from which node to which node you declare a Hamiltonian cycle. So let's take the problem further. What were the entries while detecting the entries were 1, 2, 3, 4, 5. Now we will go from this end, from the right end. This value is 5. We will use the modulo operation here because there are 5 vertices. What is the next vertex? What is the next value? 0. So 5 is made as 0. So once 0 comes here, it will stop, right? It will count. It will stop here, right? Stop means go back. Go back means we will have to start the algorithmic loop once again. Go back. Go back where? Go back to x4. What is the value present in x4? It is 4 only. All right. So we again the same algorithm. We will have to increment the value. What is the next value of 4? 5. Whether 5 exists in the previous values? No. So this value is 5. 1, 2, 3, 5. Go to the next one. Sorry, go to this side. When you come 1, 2, 3, 5, because you incremented 4 from by 1 and made it 5. 1, 2, 3, 4. What is the next value of 5? 0. Because this 0 is already there. Is there? And we'll have to check. Yes, this is very important. Is there an edge from 3 to 5? Okay, let me once again explain the thing. We reached to here 1, 2, 3, 4, 5. That means one Hamiltonian cycle is detected. Okay, the next value of this 5 is 0. 1, 2, 3, 4, 0. 0 means stop and go back. Go back where? To x4. We come here. We increment the value. It becomes 5. So what are the values? 1, 2, 3, and 5. Okay. So we will have to check, is there an edge from 3 to 5? Let's check from the adjacency matrix. 3 to 5, there is no edge. It is 0. So when there is no edge, so this is not a valid entry. We will have to change this value. What is the next value of 5? 0. So it also becomes 0. All right. So when 0 is there, we will have to go back to this position. So once 3 is there, what is the next value? Next value is 4. We put 4 here. But we will have to check whether there is an edge from 2 to 4. Let's check whether there is an edge from 2 to 4. 2 to 4, yes, there is an edge. So we write 4 here. And we take the graph further. From 2 to 4, we draw a node like this. All right. So come back to the next position. This is 0. Incremented 1. It's a duplicate. Incremented to 2. Again a duplicate. Increment to 3. Yes, 3 is a valid entry. But we will have to check whether there is an edge from 4 to 3. Let's check whether there is an edge from 4 to 3. Yes, there is an edge from 4 to 3. So this is a valid edge is there. All right. We go to the next position. Once we go to the next position and we draw from 4 to 3, this node also. So let's go to this entry, 0. We will make it 1. 1 is already there. We will make it 2. 2 is already there. 3. 3 is already there. 4. 4 is already there. 5. 5 is a valid entry. But we will have to check whether there is an edge from 3 to 5 or not. Let's check from 3 to 5. There is no edge. It is not a valid. No edge is there, so it's not a valid entry. All right. Then it's not a valid entry. So 5 is not 5. What is the next value of 5? 0. So when it becomes 0, it goes back here. When it goes back here, let's look. Let's increment this now. We'll make it 4. 4 is already there. It's a duplicate value. When 5. So let's look at this. 1, 2, 4, 5. Okay. So 5. Whether there is an edge from 4 to 5. Yes. Let's check whether there is an edge from 4 to 5. 4 to 5, there is an edge. Yes, there is an edge. So when we made this entry, 1, 2, 4, 3, actually there was no edge, so that was not a valid entry. But there is an edge from 4 to 5. So 4 to 5 is now the root becomes from 4 to 5. This node is killed, right? So here the value is, here the entry is 5. We go to the next one. 0, 1, 2, 3. 3 is a valid entry here, right? So once 3 is a valid entry, 3 is a valid entry. In that case, Whether there is an edge from 5 to 3, let's check whether there 5 to 3 there is no edge. Again, this is not the correct correct traversal path. All right. So then, I mean, the algorithm will repeat like this. The what you are looking for in the algorithm, right? And then you will see 1, 2, and if you go on repeating like this, you will find 1, 2, 5, 4, 3 is a valid entry. 1, 2, 5, 4, 3, and earlier we found 1, 2, 3, 4, 5, 1. Right? You go on doing like this, you will be able to find the Hamiltonian cycles. The important point in the algorithm, let me once again explain. We take in a graph, when we have to find, for example, in this graph, how many Hamiltonian cycles are there. We are available with the adjacency matrix. We will take an array. We will fix the starting vertex as 1, as I have did here. Then in the next entry, we will increment the values. We will start in the 1, it's a duplicate entry, 2 is valid. So we come to 2. Then we go to the next entry, 1 not possible, 2 not possible, we go to 3. 3 is a valid entry. Going like this, we come to 1, 2, 3, 4, 5. And we are also checking whether there is an edge from the present entry to the previous entry. So this is, and when we do, this becomes the Hamiltonian cycle. Then we increment 5. What is the increment? Because it is taking modulo operation, 5 will become 0, right? When 5 will become 0, the entries are 1, 2, 3, 4 like this. When 0 is there, we will stop and we will go to this value and start incrementing it. It is already 4, we will increment it to 5. 1, 2, 3, 5. And we will check whether there is an edge from 3 to 5. No, there is no edge. So in that case, this value is again incremented. This will become 0. Once 0 is there, we'll have to go back here. 3. Now increment this. 4. It becomes 4. 1, 2, 4. Right? And start. It's a valid entry. An edge also exists from 2 to 4. And we are at the same time drawing here. Drawing is not that important. Right? Once all the entries of the X matrix are filled, that becomes a Hamiltonian cycle. All right. And you go on repeating like this, you will find the Hamiltonian cycle. And let's look at the code, because this is also very important. You will be able to understand the algorithm properly. Algorithm is, there are 2 parts of the algorithm. One is the Hamiltonian. We are finding the Hamiltonian cycles. All right. And the second part is the next vertex. What is the next vertex? As we were doing here, we were taking 3rd vertex, then 4th vertex, then 5th vertex. So a loop is, so therefore this separate function is written, which is the next vertex. Now let's see. Hamiltonian, we are using the do while loops. So what it has to do, first of all, it will call the vertex. It will call this function next vertex. So it goes to next vertex, right? Xk, this is the vertex value. Entry is being made in the array. So we will increment the vertex and we will take the modulo operation, mod of n plus 1, right? So next value. Next value is, we are taking the mod operation, because after 5 it becomes 0. So when after 5 it becomes 0, that means we are taking the modulo operation. So this will give the next values. Now we are checking what? We have to check 3 things. First thing is that, now if xk is 0, then we will return. In the end, when it becomes 0, we will return. As I said, when it becomes 0, we will stop. 3 things we will have to check. First thing is that there should not be any duplicates, right? That is checked. And second thing we have to check whether there is an edge of the present entry to the previous entry. This line of the code, if g, which is the graph part, xk minus 1 comma xk, this is the edge. Whether it is not equal to, when it is not equal to 0, that means the edge exists. But if it is 0, that means there is no edge. So this is checking whether the whether the present vertex from the previous vertex there is an edge or not, this line of code. Now this loop for j equal to 1 to k minus 1, k is the present value, k minus 1 are the previous value, whether the present value is equal to the previous values or not. If it is equal, break, because we have to avoid duplicates as we were doing in the algorithm. So it will check for duplicates. This line of code this third line of code will check for the edge. This for loop will check for the duplicates. And the last entry, this will check x of n, whether there is an edge from the last entry to the starting vertex. X of n comma x of 1, because we took the starting vertex as 1, whether there is an edge from the last vertex, which was 5 in one of the Hamiltonian cycle, whether there is an edge from 5 to 1 or not. If it is not equal to 0, that means there is an edge. So we will return with these values if it is true, and if it is true, if xk is 0, it will break from here. But because k is not, because at this time when k was 5, it will come to this position, this if statement, k is equal to n, yes, because k becomes 5 as in the example, then we will print the we will print the Hamiltonian cycle. We will print the values of the array from 1 to n. That means we will print 1, 2, 3, 4, 5 is the Hamiltonian cycle. All right, and then it goes back to if it is true. Like, I mean, this is taking the Hamiltonian cycles. This portion is taking the next vertex in the array, as we were experimenting with these values. All right, and 3 things are checked in the algorithm. The first thing is that there should not be any duplicates when making the entry in one of the positions in the array. There should be an edge from the present entry to the previous entry, and for the last value of the array, whether there is an edge of the last value to the starting word. That's what is checking here. These are usual statements. So based on this algorithmic approach, you can write a code of detecting how many Hamiltonian cycles are there in the graph or not. All right. So this finishes the Hamiltonian cycles part, how you can detect the Hamiltonian cycles or not. This is basically, and if you will complete this graph, this is basically depth first search. Please complete the graph and detect, and practically based on this algorithm, go on changing the values as I have told you in the array, and find out how many Hamiltonian cycles are there. You will be able to understand the procedural part and everything, and go on drawing the depth first search tree also, and while finding the Hamiltonian cycle. If you find any difficulty, or if you have any questions, always welcome, you can come back with that. I have given you the code part also, a little bit source code also, so that you can write the, because in the exam you have to write the algo part at least. This becomes the algo part. Now in today's lecture I will cover one more thing, which is what is known as the complexity theory. This is the last part of your syllabus, though I will cover some more algorithms, right? Like traveling sales, branch and bound, then graph coloring is there, then Belford, that all pair shortest path algorithm. So like that, I will cover some more algorithm, but let's look at what is complexity theory. You must have come across with these things, NP or P class of problems, or NP class of problem. Now what is a P class of problem? P means polynomial class of problem. What is the polynomial class of problem? Right? Any problem which is solvable in polynomial time comes under the category of P class. Solvable in n to the power k. If the complexity of the problem solution is O of n to the power k, So that means it becomes a polynomial time where k is a constant and is a size. Suppose there is a problem and it is solvable in, let's say, O n square, O n cube, O n 4. All these are polynomial problems. All these are P type of problems. Now, what are NP problems? These are NP problems. First of all, are where the solution does not exist. Number one. But if some solution exists, you cannot. The point is that for NP problems, and these problems are not polynomial problems. These problems are basically exponential time problems. Now, but if the solution to a problem exists and the solution is verifiable in polynomial time, it does not mean that it takes actually, the solution takes polynomial time. No, the solution exists. It normally takes exponential time, but if you want to verify whether this solution is correct or not, if you can verify that solution in polynomial time, then this is an NP problem. This is this is what is n here. I will explain. Now, if x is a problem, the algorithm written can be verified in polynomial time. It is NP problem. Now, all P problems are subset of NP problem, because all polynomial. This will certainly take more time. These are exponential problems. So any polynomial problem becomes a subset of the exponential problem. So P is a subset. That's how we draw this part of the graph. The first circle, P is drawn as a subset of NP. Right? Now, what is NP hard? There is no known polynomial time solution, not solvable in polynomial time. The problem which are not solvable in polynomial time, these are NP hard problems. We call those problems as NP hard problems, right? Even they are not verifiable in polynomial time, not solvable in polynomial time, these become NP hard problems. I will explain a little more. So P is a subset of NP, NP hard. Now, what is NP complete? Because usually, you know, you must have seen this graph number of times, but where the problem comes is understanding of what is NP complete and what is NP hard. Now, what is NP? Problems which are NP hard as well as NP are called NP complete problems. Now, what is the meaning of those problems which are not solvable in polynomial time, right? But if any solution for this problem is given to us, it can also be verified in polynomial time. NP problems are what? The solution of the problems is verifiable in polynomial time. NP hard problems are what? Solution does not exist. What are NP complete problems? If for an NP problem, solution exists and that solution is verifiable in polynomial time, it becomes NP. Those are NP complete problems. Let me explain what is the meaning here. So from this algorithm, let's say an algorithm is there and search with these parameters to be passed, and J is equal to choice. What is choice? I don't know. But this choice part of the code will give me the index of search. And if, don't worry about what is choice. Choice does not exist. But the point is that, so it's basically NP hard problem. No solution exists. But if somebody says that in future, somebody will write this part of the code choice, and this part of the code directly gives me the index of search, then I will be able to solve this problem in O1 of time. Who will do this choice? Somebody else will do in future and write the code for this. But this man at this time has assumed that if choice exists, if this part exists, and it will directly give me this index, my search will be solvable in polynomial time. This is right. The problem was NP hard problem, but he made assumptions that somebody will give me this type of theory of choice. Somebody will give me this subroutine. I will be able to get the index. So he declares this problem as NP complete. NP hard problem has become now an NP complete problem, but it is still an NP problem, right? And two more terms are there. One term is deterministic, one is non-deterministic. What is deterministic? When we write an algorithm, we know each statement. When we know each and every statement of the algorithm, that algorithm is known as deterministic algorithm. What is a non-deterministic? What is a non-deterministic algorithm? When we don't know that when we don't know some part of the, we do not know a portion of the algorithm. That is the solution of that part. We assume that if it exists, either today, tomorrow, years after, I don't know. But if it exists, then it is solvable in polynomial time. You must know what is an NP hard problem. No solution. What is an NP complete problem? I make an assumption that if somebody will do this, I will be able to solve this in polynomial time. That is NP complete. What is NP? NP is the solution is verifiable. What is an NP problem? Takes exponential time, but solution is verifiable in polynomial time. What is P type? The solution exists for polynomial, right? This graph is actually very important. I will probably discuss this graph maybe in the coming lectures also, maybe sometime in the coming lecture, so that if something is left, we can discuss it. All right. Now, that's what is all about today's lecture. Now, choice, let's look at this page. Now, choice is a non-deterministic statement. This is very important. Nothing exists for this choice, but the person has made the assumption that if the choice subroutine will give me the index, my algorithm complexity is O1. The solution is known as non-deterministic polynomial time, or NP complete problem. All right. So you must understand this graph. What is the P type of problem? What is an NP problem? What is NP hard? What is NP complete? Probably I will come on more. I will discuss a little more about these things also, if the time will permit. We have a lot of time, so we can discuss. There is no issue. This forms the basis of a subject in computer science, which is known as the theory of computation. All right, and this forms one of the portion of theory of computation, which is the complexity theory. I have just tried to introduce what is complexity theory, right? Actually, a lot of research is going on. For example, the traveling salesperson problem, as we were discussing, it is an NP hard problem, but now people have assumed it is an NP problem. Basically, NP problem means it takes exponential amount of time. It's an NP problem, right? It's not NP hard because the solution people have found, but it's not available in polynomial time. People today are also doing research on traveling salesperson problem only to find a polynomial time solution. All right, so we'll stop here. And if you have any questions, you can post your questions on email or WhatsApp, or maybe one Zoom lecture I will take for questions. Thank you.